Alright, so let's look at solving this problem. We have a given amount of mass, 3.3 kilograms, and we're told that it's air. When you see air, you're thinking ideal gas. Very rarely is air not treated as an ideal gas. It's a very good ideal gas, or the model fits air, describes its behavior very well. It's contained in a piston cylinder assembly and executes a Carnot power cycle. Right there's a lot of words, or a lot of meaning in these words. Basically, the Carnot power cycle, where you have air in a piston cylinder assembly. I'm only reviewing this. You should have already studied it, so I'm going to go a little fast on this. You can sketch it on a PV diagram. This can be specific volume or total volume, either way. And you start somewhere in the cycle, and you're going to go along a line of constant temperature, and then jump to another line of constant temperature by compressing and compressing, then come through an expansion along a line of constant temperature, and then I need to stop it earlier than that, and then come down and expand. So I know I've sketched this with 4 processes and 4 states. So let's follow the textbook. The numbering really is arbitrary, but they start with 1 here, then 2, then 3, and then state 4. So if you think about it, everywhere along this line from 1 to 4 is a temperature is equal to a constant, and it's our low temperature. And anywhere along the line from 2 to 3, the temperature is also a constant. I try to change color so it's easier to see, but it's high temperature. So the temperature at state 2 is the same as the temperature at state 3. Likewise, the temperature at state 1 is the same as the temperature at state 4. Okay, so when you're going from state 1 to 2, it's being compressed, and it's happening adiabatically, meaning the heat transfer is 0. So 1 to 2, that's what you have to understand when you see the Carnot vapor power cycle with the air in a piston cylinder assembly, all of this. So you can say, okay, 1 to 2, what is that process? Adiabatic compression. All right. Then from 2 to 3, well, what's happening with the volume? Look at the volume diagram. Are you expanding, or are you being compressed? Well, no, it's expansion. Now, is it being adiabatic, no heat transfer, or is it constant temperature? Well, it's constant temperature. We call it isothermal. Isothermal expansion. And then from 3 to 4, another process. What's happening there? Well, you're not allowing any heat transfer, so it's adiabatic. And is it expanding? Sure, it's expansion. All right. And then from 4 back to 1 to close the cycle, it's isothermal at the low temperature. And then it's compression. You may find another textbook numbers the states a little differently, but I'm trying to be consistent with our textbook. Okay, that's all packed in these first few words. Then they tell us the maximum and minimum temperatures are 600, so right here, 600 Kelvin, and the minimum 400 Kelvin. Okay. The heat transfer to the air during the isothermal expansion is 90 kilojoules. Well, where is my isothermal expansion? Well, I'm glad we put this down here. It's right here. So what they're saying is that, let me do this. I'm trying to organize information. What we're going to do is we're going to find that it's helpful if we make a table of properties, as well as a table related to the first law. A lot of times I'll talk about, I'll just call it the first law table. Okay, so for our properties, what states do we have? You just start right here. State 1, 2, 3, 4. Okay. All right, what properties of interest? Well, often we're interested in pressure, maybe in bar, kilopascal, megapascal, whatever you have. And then the temperature, Kelvin. I like to kind of put them in this order. It's like, hey, this is one of the first properties we really studied in Thermo 1, pressure, pressure, pressure. What was the second property we studied a lot of? Temperature, temperature, temperature. And then the obvious one would be for this one, volume, meter cubed. And then you could have other properties, let's say internal energy in kilojoules per kilogram. Now, having solved this problem before, that's all. I mean, sometimes you don't know what you have, and maybe you need to put quality, but it's air, so air is not going to have a two-phase mixture. But if it was steam or refrigerant, quality may be, in the table, or enthalpy. But I just know that these are enough for this problem. So now, actually, pressure, when you look at it, it's really, I'm going to leave it there, but it's not needed at all. Let's go ahead and put our temperatures in this table and populate it. And then we're going to create a table to help us organize the information about the first law. But let's populate the property table first. So what about the temperature at state 1? Well, it's the low temperature, isn't it? I don't have to repeat the Kelvin because it's in the header of the table. And then we have the 600. Boy, that's a bad looking 600 over here. 600, right? It's 600 and 400. Okay. And then 600 for state 3, and then 400 again for state 4. Again, it's just that the pressures are not needed. Okay, now let's do this. Let's make a table of my first law information. And what I like to do is make a table where I'm saying I'm going to put either a change in the cap U, which is just the mass times the change in the lowercase specific internal energy. Okay, and then I'm going to put Q, and then I'm going to put work. So those are my 3 columns, and I leave a little extra room, and because I lined it up right here for the process 1 to 2, this really, I could even extend it. Let's just call this my process. Process 1 to 2 with the description, it's adiabatic compression, blah, blah, blah. So I would put right here my mass, then I would put U2 minus U1 for that. Okay, and then I would say, okay, my mass, and then might be U3 minus U2, all right? And then the mass times the change in the specific internal energy, U4 minus U1, and then the mass, you got to go slow right here because the final state after the end of the process going from 4 to 1 is U1, not U4. Did I mess that up? That's 3. Minus U4. There you go. Let's take a look. 1 to 2, 2 to 3, 3 to 4, 4 to 1. Yeah, I think that's right. And then I like to write this like this. Q1 to 2, Q2 to 3, Q3 to 4, Q4 to 1, and then the work 1 to 2, the work 2 to 3, the work 3 to 4, and the work 4 back to 1. All of these have units of kilojoule, kilojoule, kilojoule. And really what it is you can see the line here. It's like this and like that. Like the change in U for the process 1 to 2 is equal to Q1 to 2 minus the work 1 to 2. And then the first law for the second process from 2 to 3. There you go. Then there you go. And there you go. But I don't put those in the table. But that's helping me why I put the table like this so I know what's going on. Now, I've kind of flushed out the table very generically. Okay, but I have some information. I can replace some of the values in this table with numeric quantities. And the easiest is to think about what's happening from 2 to 3. If I go from state 2, here, let me try to emphasize that, to state 3, okay, does the temperature change? No, the T2 and the T3 are the same. Well, if that's true, and for air as an ideal gas, we recall 3 things for an ideal gas. P and V is equal to MRT is a good ideal gas equation. U is a function of temperature only, and enthalpy is a function of temperature only. Well, if the internal energy is a function of temperature only, and the temperature didn't change between 2 and 3, can't I say that this is 0? Sure, it's 0. And then we look and we say, well, what about the process from 4 to 1? Wasn't that isothermal? Yeah, it is. And so this also is 0. I'm just trying to, let's say it's 1, 2, 3, 4. So I have 12 values in this table that I'm trying to fill out, and I just figured out 2 of them are 0. Okay, those were the changes in internal energy. Now we focus on what about the U's, the Q's, the heat transfers. Well, 2 of the processes were adiabatic. What does adiabatic mean? No heat transfer. So this one, see, at the process 1 to 2 is adiabatic compression, and then the process 3 to 4 is adiabatic. So it's like, ooh, this is great. So half of our delta U column and half of our Q column are zeros. How about half of our works? That would be great. But if you look at it over on a PV diagram, you're always having some change in volume. You're either in the compression or expansion or compression. So no, all 4 of those are not 0. They need to be calculated or given in the problem statement. Okay, so a lot is here, and I've only read one whole sentence. Let's try and read the second sentence and then use that information. The heat transfer to the air during the isothermal expansion is given. Ah, good. Well, where is that isothermal expansion? Is that from process 1 to 2, 2 to 3, 3 to 4, 4 to 1? That's why I think the table is very helpful. So you have an isothermal expansion of 90 kilojoules. You come down here, you read, oh, it's from 2 to 3. That's my isothermal expansion. So I can replace this one, Q2 to 3, and I'm just going to go ahead and put the number in. And I mean, well, I could put Q2 to 3 is equal to 90. That would be fine, or just replace it like we replaced the other ones with 0. Okay. And let's continue to read the problem statement. At the end of the isothermal expansion, the volume is 0.35 meter cubed. Okay, so the volume at the end of the isothermal expansion, well, what's at the end of the isothermal expansion? Where's that? State 1, state 2, state 3, state 4. Well, it's state 3, isn't it? Isothermal expansion, the end state is state 3. So we come up here, and the V3 is 0.35 meter cubed. Okay. Assume ideal gas model. That's right. Thank you for the reminder. These are the 3 things. PV is equal to MRT. U is a function of temperature only. H a function of temperature only. And we want to determine the thermal efficiency of the cycle and the volume at the beginning of the isothermal expansion, and then the work during the adiabatic expansion. Well, we know that it's a Carnot power cycle. The thermal efficiency, the most important, one of the most quoted, the most used equations, maybe on an exam to see if you've taken thermo before, maybe in the FE exam or the EIT exam. They just want to see if you know that the thermal efficiency of a heat power cycle, is a heat engine, is given by the Carnot efficiency 1 minus the low temperature over the high temperature, and they must be in absolute scale like Kelvin. So it's like, oh, we got this. This is 1 minus, what's my low temperature? Well, it's 400. What's my high temperature? 600. So 1 over 4/6, isn't that 2/6? And what is that? 1/3? So the thermal efficiency is 33.3%. That's the answer. For part A, there's no units on this 33.3%. It's dimensionless. It's an efficiency. Okay, so there you go. We finished part A. All right. Now they ask, what is the volume at the beginning of the isothermal expansion? Well, first of all, you got to figure out what state that is. Is that state 1, 2? Well, we already figured out state 3 is at the end of the isothermal expansion. So they must be asking us to solve for V2. That's what they ask us to solve for. What is the volume at the beginning of the isothermal expansion? Okay, well, here's our answer. We know what we're going to calculate. Before I calculate it, let me just compare. If I wanted to, I could come under here and I could say that was 0.35 on this V scale in meter cubed. And then the answer that I'm looking to calculate is going to be down here. Maybe that's, I know I didn't draw it too good, but it's going to be your smallest volume. Here's V1, here's V2, and that V2 is 0.2987. That's my answer I want to calculate. Okay. All right. How do we do that? Well, what you can, what the theme is to use the first law of thermodynamics. Okay, right here we've written the first law of thermodynamics in a table for the isothermal expansion, for the process from 2 to 3. Let me just kind of put those blue marks in. It's like the change in the U is equal to the Q minus the W. Well, at this point, what you can do is use the first law. You can calculate or find or determine that 0 is equal to Q 2 to 3 minus the work 2 to 3. Hence, therefore, the work 2 to 3 is equal to Q 2 to 3, which is 90 kilojoules. So sometimes what you can do is just say, okay, this is 90 kilojoules right there. Now that I know the work 2 to 3, is there any way that I can calculate that volume at state 2? I know I'm going to scoot down and I'm going to lose this problem statement, but I really want to do this so you understand. So on a PV diagram, I have this process. I'm just focusing on state 2 to state 3, and it's some expansion process where the temperature is a constant at TH. Okay? And the area under the curve is the work. And we know the magnitude of the work. We just said it's 90 kilojoules. Well, how would I calculate it analytically? Well, it's the work 2 to 3 is equal to the integral of PdV. From where? Volume 2 to volume 3. Hey, haven't we done this before? Sure we have. We've done it for the case where PV is equal to a constant, or PV to the exponent n is equal to a constant. This is sort of a polytropic, and then this was our n equal to 1 case. But we're doing this for an ideal gas that's isothermal during this expansion. So we remind ourselves, I wrote it up there, that PV is equal to mRT. Okay, is the mass of the gas trapped in the piston cylinder assembly changing during? No, it's constant mass. Is the gas constant? No, just look at the name. It's constant. It's the gas constant. I know it's for air, so it's R bar divided by the molar mass. How about the temperature of the gas? Is the temperature of our gas changing as we go along from state 2 to state 3? No. So really, PV is equal to a constant. So if PV is equal to a constant by the ideal gas equation, then PV, we've done that integration. We've solved this problem where we've integrated before. And so we just remember, oh, this is where the case n is equal to 1. What is my result coming out of what chapter? I forget, 2, chapter 3. It's going to be that we have the P2V2 natural log of V3 over V2. Or you could say, no, I thought it was P3V3 natural log of V3 over V2. They're both the same because the P2 times V2 is equal to the P3 times V3. So these are the same equations. And oh, by the way, somebody says, I don't like that form. The form I really like is mRT high, because it's constant temperature and it's our high temperature. It's our, for this problem, 600 Kelvin. Natural log of V3 over V2. Maybe we students get confused because there's so many ways of writing the same information down. So the only thing that we really don't know in this equation, we know the mass and the R and the T and the work, and the final volume, V3, we just don't know V2. do we? Well, it's a little bit of algebra. Now, I know this is what throws students for a loop too. It's like, man, I forgot all my algebra. Well, you can't do that, right? Let me go slowly in this algebra right here. So what we would do is we'd say the natural log of V3 over V2 is equal to, then we would have the work 2 to 3, which we know is 90 kilojoules, divided by the mass, whatever that mass was, something like 2 or 3 kilograms, I even forgot. The R, which is R bar divided molar mass of the air, and then that temperature, the 600 Kelvin, TH. All right. Well, I can then exponentiate both sides and play with the math, and you get that the initial volume V2 is equal to V3, the exponent of the minus work 2 to 3 divided by MRTH. And if you need to take a few steps to do that algebraically, make sure that you can do it algebraically and not make an error. Okay. So now what we're going to do is we're going to insert our numbers. Maybe I should scoot down even more. Okay. And then we're going to solve. So 0.4 meter cubed. Now, when you take the exponent of whatever is inside, it has to be dimensionless. So you can check that, and it will be for this problem. So let's go ahead and minus the 90 kilojoules. The mass for this problem, I forgot what the mass was. Let me look it up. Which is 3.3 kilograms. Then we had, I'm going to put it R bar, 8.314 kilojoules per kilomole Kelvin. And then I'm going to put the molar mass up here of 28.97 kilograms per kilomole. All right. And then our temperature was 600 Kelvin, close parent. Now, Kelvins go. 1 over kilomoles go. The kilograms go. And the kilojoules go. It is truly dimensionless. Okay. Now, when you calculate it, you find that V2 comes in at 0.2987 meter cubed. I encourage you to do that on your calculator to verify. That's the answer for part B. A lot of work. Okay, now we've calculated that volume. Let's go back and look at what the last part was. What is the work during the adiabatic expansion? Well, this is process 3 to 4, isn't it, our adiabatic expansion? So what is our work there? I look at it, and it's not an isothermal expansion. In the next chapter, we'll actually come up with an algebraic expression explaining the relationship between P and V along this path. It'll be like P, V to the K is equal to a constant, but we're not there yet. We are not there yet. So you can't analytically calculate that work by the integral of P dV. So what do? I can look up the changes in the specific internal energy, or I can calculate the specific internal energy going to table A22 in our textbook. So U is only a function of temperature, and we go to the table and we can find U at a temperature of 400 is 286.16. And then U at a temperature of 600 is 434.78 and 434.78. And then back to 400 is 289.16. We have those U's, hence we can come over here with our mass. Our mass was 3.3. We have our U2 and our U1. We can calculate this change in cap U. Let me try and put that in right here. Leave it in red. The change in the internal energy turns out to be the 490.45. All right. Well, what did that buy for us? Well, that bought for us that when you look at the equation for the first law for the process 1 to 2, you have delta U equal to Q, which is 0, minus the work. And so what we can deduce is this work 1 to 2 is negative 490.45. How do we do that again? The first law for the process 1 to 2. We're able to calculate what's on the left-hand side of the equation, and then we have equal sign Q and then minus the work. Okay, this MU4 minus U3, that's going to be negative 490.45. Do the first law for the process 3 to 4, and then this is equal to plus 490.45 kilojoules. Wasn't that our question? What is the work during the adiabatic expansion? Yeah. Okay. Well,